All right. So this morning we are going to be doing a very basic design, going through what is expected on electrical drawings and showing the bare basics and the introduction of what a overall plan set should look like. This is actually a real world scenario. I've got call my client that has a 20-foot by 40-foot shell of a building, and they are wanting to make this into a cabin in the middle of nowhere. So obviously I've already got the shell pre-set up. They're going to eventually have a restroom right here. The kitchen is going to be over here. They've got a pony wall right there, and then obviously two doors that enter into the space. This is the three-dimensional version of that, which you can see. Pretty simple and easy, nothing major. So we're going to be laying out, a couple receptacles, panels, whatnot, into here. And then from there, we'll show how to get the sheets set up, or what sheets are expected on any general basic electrical plan set. Any questions on that so far?
No questions.
Cool. All right. So let's go ahead and start off with, okay, we've got this. Oh, actually, I did want to go into, I started this from scratch, from like a blank Revit, file new something new model from scratch. There's a couple things I've already done, including setting up the electrical settings. So if you've never done that, let me get there again because I went kind of fast. So MEP settings, electrical settings, bring this up. All right. So when you start from scratch, or if you're having to modify based on project specific information, this is where a lot of stuff's going to be at. Generally, like voltage definitions. This was entirely blank. I had to put in this information. Values, obviously, I kind of threw in a random minimum, maximum. I highly recommend putting in the proper ones based on your location, wherever you're at in the world for YouTube, because for us here in the States, ANSI C Charlie 84.1 defines what the utilities can do plus or minus on their minimum and maximum voltages, what's acceptable. So it's usually like 3% if I remember right. So, whatever 120 plus or minus 3% is, that's what these two values should be. So on and so forth. So yes, I've defined voltages here. Probably should have put 240 in here as well, but I didn't. And then distribution systems. Here in this project, we're going to be using 208Y and 480Y. There's obviously 120, 240, which is single phase, which we've talked about. And then 240 delta, which can also be a high leg. So 240, 120 is what you call that high leg. All right. Questions on that one?
No questions.
All right. Load classifications in here, so we will probably get into that after a while, maybe on a different project, not on this one. And then panel schedules, this is incredibly helpful to know that, hey, I can modify panel schedule information in here, because a lot of people don't realize that. All right, so that's the very basic of that. So let's go ahead and start just dropping in a couple things. So I want some duplex receptacles. Yeah, we'll go with that. You can see them going in over here on the three-dimensional version, just so you can kind of see what we're doing. If this is going to be the kitchen, there's going to be specific requirements per NEC in the kitchen itself for what outlets, receptacles are required. Same thing in the bathroom. It's going to have their own, the NEC is going to tell you what is required for a bathroom, kitchen receptacles, so on and so forth. For now, I'm just kind of sticking them in there so that we can kind of see what all we're looking at. Right. So that's site plan. Let's go to lighting plan. We're going to drop in a couple lights so that you can see those. While the receptacles are 120, I'm going to bring in the lights at 277. So the reason for that is because our client has a 480 volt generator. He wants to be able to connect this 480 volt generator to this building without having to have a whole lot of stuff. We won't show the generator connection, but the idea is he's got a 480 volt generator. He wants to be able to plug right into this. And since 277 lights are much more efficient than 120, that's why we're doing 277 volt. I'll just kind of throw some random stuff in here because why not? So that's not what I wanted. There. Come on. All right. So we have lights and receptacles. Whatever other HVAC equipment, all that stuff, you would put it in at this point. You know, whatever mechanical equipment that needs to be powered, or depending on the project, whatever it is, EV chargers. Now is when you would do it. You get in all of your electrical stuff into the model first. Okay. Obviously, we did that very quickly. Most of the time, it's going to take a couple of hours, if not a couple of days, to verify you've got all the equipment in there. So as you're going through, look at the mechanical sheets, look at the plumbing sheets. You want to make sure that you've got, you know, an outdoor unit powered. You want to make sure that you've got the hot water heater powered if it needs it, or if it's gas, or if it needs a receptacle and it's gas, so on and so forth. Look at mechanical and plumbing at the same time you're doing your electrical sheets to make sure that you're all matched up. Right? So from there, once you get all of everything powered up, I'm sorry, put in, we're going to start dropping in our panel boards and transformers and whatnot. So let's start off with, let's start off with the 30 kVA transformer. Just bring a dry top over here. That's the lighting.
You normally get like do you choose the layout of the receptacles, or is it is it mainly the like client who kind of tells you where things are to know where you need them?
That's a great question. The answer is mostly you, but the client can have specific requests, or the architect for that fact.
Gotcha. And same with lighting, like lighting layouts. The architect could be laying out the lighting, but you also could be laying out the lighting. It really just depends.
Ooh, that's a little bit more complex. So we'll call it power. You know, receptacles, disconnects, whatever else. The NEC has a lot of requirements of, if you're in a living space, for instance, you have to have a receptacle within 10 feet of each other.
Okay.
Something to that effect. If you're in a hospital, in an OR room, you have to have 24 or 36 receptacles, you know, whatever it is. If you're outside by an HVAC unit, you have to have one. Like the NEC is going to drive heavily the minimum number of receptacles.
Like all of your, so follow the NEC for any requirements that are needed for receptacle layouts, lighting layouts, and so forth. Like, or also if a client's like, hey, I have computers over here, I need X amount. Like, is there you can't have too many in a specific location? Like, or is it just you need to have at least this many?
You need to have at least this many.
Okay.
So yeah, that's a great question on the receptacles and other power. And it's not just the NEC. NEC will direct you to other locations, or depending on what state you're in. Like North Carolina, South Carolina, I think they could follow FGI guidelines, something like that. There's a couple other states, but there's additional requirements for specific locations, like nursing homes, hospitals, wastewater treatment plants, stuff like that. So yes, NEC is primary, and then whatever's applicable to your state based on your project.
Gotcha.
And when it comes to lighting, yes, architects will normally lay out lighting, but you don't have to follow it. You're actually not supposed to follow it to the T.
Gotcha.
The reason for that is because they're basically saying, this is the type of lighting that I want, because they're architects. Like they
want it to look nice.
Yeah, they're the artistic people. They're the pretty people. They're butterflies, whatever you want to call them. Whereas engineers are like, no, it's basic math. It's basic this.
Like,
don't
there's
be
a
dumb.
rule for everything.
Yeah, there's a rule for this. So if you've ever seen any buildings from like Soviet Russia, 1980-ish, those were built by engineers, not architects. They're literally brick cubes with a couple of windows here and there. Like, they're basic. And that's what I like. It's not pretty. It works. Very functional. So, yeah.
Nice.
So architects will throw in some lights. They will give you the understanding of what type of lights they would like. Like, do they want 1x4s, which is what these are? Do they want 2x4s? Do they want recessed can lights? Do they want pennants, which is, hanging lights? What do they want? Okay, that's the idea. They're trying to tell you, oh, we want 1x4s in here. That's when we come in and say, look, you give us the idea, we get it. Now we have to lay out the lights in order to meet the lighting requirements. Okay, there are other codes out there that have lighting requirements that we have to follow. Like office buildings are supposed to be 40 to 50 foot candles 4 feet above finished floor. Exit egress paths have to have like 0.1 foot candles when all the power's out. So we have to have like emergency lights, like bug eyes and whatnot. So while the architect goes, we want this, engineers go, you actually have to have this based on code requirements. And I literally just kind of threw this in here because of experience. So I kind of just know how this would lay out. A couple of things. Let's do some math because I like math. Here we go. This is what I was looking for. If I've got a 30 kVA transformer, 3-phase, how many amps on the 480 side can this thing handle?
Ooh. You said 30 kVA and the voltage is 277?
480 on the primary.
It's you do the 30 time you do 30 divided by root 3, like the square root of this, like the square root of 3, 480 square root of 3, right? 480. I can't think of what root 3 is. 1 point something.
1.732.
1.732 times 1. Oh. Okay, so you do the 30 kVA, which is 30,000. Is it 36?
Yes, 36 amps.
Give me.
All right.
Yes.
So how many
Sorry,
amps?
crappy calculator.
No, you're good. So for the people on YouTube, how did you get 36 amps?
So we have 30 kVA, which is 30,000 volt amps, which is equal to amps times voltage. Your voltage is 480, and because it's 3-phase, you have to multiply it by root 3. So then you take your 30,000 and you divide it by the 480 times root 3, and then you get your amps. That's how I did it.
Oh, okay. I do it 30 kVA divided by 480 divided by root 3. Never thought about taking 480 times that, but yeah, that works. So it's just dividing out 30 kVA divided by 480 divided by root 3. And you can plug that into any calculator and it gives you 36.1 amps or 36 amps.
And this is more of a question. Anytime it's 3-phase, even if it's not because it's 480/277, you still have to use the 480 number to find the amps. Correct?
If you
there's also the 20, what'd you say, 208? Oh, 20, it's a 208 is also 3-phase, right?
correct.
So you do like if this wasn't 480 and it was 208, you would just do the 30,000 divided by 208, then divided by the root 3, right?
To get so the answer is yes, but what amperage does that give you?
Oh, I didn't do it. 30,000 divided by 208, and then divided by 1.7 something.
1.732.
83.27.
All right. So what is that amperage? Like, what does that mean? 83 amps. What is that?
I don't know.
Okay.
I feel like it's it's not a quick trick question, but I think it is.
It's not. It's simple. And that's why I asked it. I've got a
Because
30
you clearly
kVA
have more,
transformer.
you have more amps. You clearly have more amps when you have lower voltage, which there's a reason for that because we've talked about it. Like 480, like you have what is it? More in like mechanical terms, like you have more pressure by having a higher voltage than a lower voltage, so it can like the current can travel further. Is that why you have more?
Uh, so you're familiar with the equation P1V1 is equal to P2V2, right?
Yes,
Okay,
it's just a
so if
ratio.
exactly. So if you're increasing pressure on the left, the volume on the right goes down.
Yes.
That,
So higher
that's
flow, so higher, like when the voltage went down to 208, we had higher current, the flow, because we had lower voltage. And we
yes,
have, at the higher voltage, we have lower flow because like the current's lower, like you said, the ratio. That's
exactly.
why we have more. Now,
Yes.
from your, sorry to cut you off, but then you said, you asked the question, like, what does that mean? Because we
You're
went
good.
from 36 to 83.
Okay. Let's make this a visual representation. If I can do this. V1, V1, V2, V2. Should be the 208 side to the 480 side. And this is the equal sign. All right, so if you want to think of this transformer as the equal sign in your P1 V1 equation, consistent because it's confusing me. There you go. All right, so P1 V1 is equal to P2 V2. Well, if I know that transition point, that what is the driving factor of this electrical equation is 30 kVA, and I know I've got 480 volts on this side, that gives me, what was it, 36 amps?
Yeah.
36 amps, right? And on here, if I got 208 volts, that gives me 83 amps. So 208 at 83 amps at three phase is 30 kVA. 480 volt at 36 amps at three phase is 30 kVA. So when I asked what is that 83 amps, the 83 amps is what the transformer can push out. The 36 amps is the maximum the transformer can take in. You can also think of this as like a pressure reducing valve. You know, what am I
Hmm.
reducing my pressure to? What am I reducing my voltage to? All right. So based on that information, on the 480 side, we can use a 100 amp panel board. And on the 208 side, what size panel board do we need? 100, 225, 400, 600.
Said 100 amp for the 480. 83, 125.
So you're correct. And
Oh,
since this
sorry,
is,
225. Sorry, I was looking at the wrong one. 225.
you're
And
good.
I'm assuming it's because of the load, like, is it, what is it? The load percent? Like there's like some kind of ratio that you have to be under or like, right? Like your panel has to be sized large, like larger by a certain percentage than what your transformer can put out. Is that why?
Close. Same concept, but instead of the panel board itself, it is actually the breakers. So,
Gotcha.
um, yeah. Uh, sorry, I'm trying to think. All right. So for the people on YouTube, like I said, I pulled all this stuff right out of the box of Revit, just so that there was no bias for whatever company we work for. There is such thing as a 125 amp 208 panel board, which is what we would normally use. But since this is out of the box, we're using a 225. So 125 would be sufficient. All we got is 225. The reason it is that instead of the 100 amp is because of the breakers in here, or in this case, yeah, we'll just say this is a main circuit breaker panel board for simplicity purposes. The MCB is most likely going to be 80% rated. And what that means is it can handle 100% of the nameplate load of that breaker for up to 3 hours. If it's 80% rated. If it's 100% rated, it can handle the nameplate rating indefinitely.
Of the breaker, not of the entire panel size.
Exactly. So
okay.
If we were to put a 150 amp breaker in this 225 amp, like I said, just call it a MCB, 225 amp MCB, it could handle 150 amps for 3 hours, and then after that it would trip. If it's an 80% rated breaker. When you specify 100% rated breaker, they are much more expensive, much longer lead time. They have their place, and they're really awesome. And I've used them on multiple occasions. But when it's a cabin in the middle of nowhere, there's not really a good reason to put a 100% rated breaker in here. So that's why we use 80% breaker and say, hey, look, we need to increase our capacity by 80%, as it were. So that would be how we would do that is 83 amps times 1.25. So at least 104 amps that we need. So that's why we would have gone with 125 amp panel board.
That doesn't mean that you cannot like, can you load the panel to 125? Like, can each breaker add up to 125 or no? Because I'm assuming we're going to get to that when we go to panel schedules. Is that correct? Because if not, you can answer later.
We will get to that when we go to panel schedules. Yes.
Okay. Sorry. Skipping ahead.
It's totally fine. I have no problem with that. These are all good and valid questions. All right. So we got a 208 panel board. Like I said, in this setup, we can do an MLO, which is main lugs only. So there's no main breaker in here. Since we're within, the code requirements distance of all of this, and there's a whole big long thing in the NEC of, does this need a breaker or not? This scenario, it does not. I'm not going to get into when it does right now because it is very long and complicated, but just so that you know, this setup, this does not need a breaker right now.
Gotcha. If I don't know if this is also another thing, but if for some reason the only thing on site is a 480 three-phase transformer, but they're wanting for some reason they're wanting to use 208, that doesn't make sense. Like, why would they? It doesn't make sense. But if they did, if for some reason we needed to use 208 because of availability or whatever, to get from that 480 to 208, would we have a 480 panel, then oh my gosh, and then the 208 panel being fed from the how would that work if we need to do that? Instead of me trying to explain it.
Right. If I'm understanding you correctly, you're saying if there's no 480 volt equipment on there, but we have a 480 volt utility transformer, do we still have to have a 480 volt panel board?
Correct.
Is that your question?
Yeah.
Okay. So in that case, if there's literally no 480 volt equipment on site, then I would set a disconnect here and then feed that directly to the transformer. Because if there's only one thing that you're feeding from the 480 volt transformer before you start feeding 208, 120 stuff, that's all you need is just a disconnect. There's only one thing. You don't need a panel board to feed multiple things.
Gotcha.
And yes, that does occasionally happen, by the way. So
you do a disconnect on the transformer?
So it would be a service disconnect.
Mm-hmm.
I just draw it right here. I was trying to look for it off screen. There, come on, there.
Because I know like a good example is like some mechanical equipment you can't always get in 480. Like it doesn't happen often, but I know sometimes it's like, okay, they only have 208 available or whatever, but we only have 480 on site. So in that case, what would the electrical have to do? Like what would we have to do to be able to provide to that piece of equipment?
Yeah. All right. So if I have a utility transformer and everything on site is 120 or 208, literally nothing else is 480. Everything is on site 208, 120. And this thing only pushes out 40 volts because it's been there for years and years and years, and the owner doesn't want to change it. What I would do is I take this 480 volt, hit the disconnect, from the disconnect, feed the transformer, from the transformer, feed that. And from here, I would feed all the loads.
Oh, like new transformer, like a 208,
Yes.
okay.
Yep.
And
Now,
and what is the disconnect exactly doing?
a couple of things. So this would be a SE rated, service entrance rated disconnect, meaning it's a lot more heavy duty than just like the heavy duty or generic general duty disconnect. It's got specific things about it that qualify it as service entrance in case things blow up. It needs to be able to sustain a little bit more. It's also going to have the uh, ground neutral bond in it, meaning this is where you would bond the neutral bus to a ground rod in the ground. Yes,
Gotcha.
here is going to have the same thing, but designated this as service entrance. Generally, that falls under that concept as well. Like, hey, give me the bond here. So
Gotcha. It is not when you said disconnect, it made me think of fused and non-fused disconnect. It's not like that. It's different, correct? Because like uh yeah, it is not the same as like you cannot say fused disconnect, not fused disconnect. That's just a disconnect. Is that
well, so
right?
technically, yes, you can. So you can technically have a fused or non-fused service entrance disconnect.
Service entrance disconnect is what it's called. And you
Yes.
call it that because like the service is the 480 transformer.
Yes. So
Gotcha.
the point of service. I'm sorry. We'll just keep it simple. The service is from the 480 volt utility transformer.
Gotcha. Like what is it called? Primaries on the other side of that 480 transformer.
Yes. So this would be like 12470, 24 kV, 35 kV, something to that effect. Yes.
And that line going from the transformer to the disconnect is secondary side. Like
Oh,
everything downstream of this is secondary side, or because there's a disconnect before this other transformer, is that all still primary, or it depends?
it's a good question. So it goes according to each transformer. So yes, if this thing, fine. All right. So if this thing is going out to the distribution line, whatever, 12470, actually, line 70. All right, there we go. So 12470, and we got 40 volt on this side. This is the primary line of this transformer. This is the secondary line of this transformer. This is the primary line of this transformer. And this is the secondary line of this transformer.
Gotcha. Okay. So primary doesn't necessarily have to mean that utility owns it, I guess is the word I'm looking for. Like I guess that the only thing that the utility, meaning like a Duke Energy or Tico or whatever, the only people that would they own typically up to that first transformer. Even though there's a primary side on the 208 transformer, that doesn't mean that they own that. But like, is that correct?
So in the short answer is there's going to be a meter right here. They own up to the meter. I was just trying to keep things simple. That's why I didn't include it.
Sorry.
No, don't be. You're
More
totally
questions.
fine. And like I told you on the front end, if we need to go down a rabbit hole, let's go down that rabbit hole.
Okay.
Excuse me. So according to the NEC, the utility is going to own obviously transformer, this line. The customer will own the meter typically, and from the secondary side of the meter, the load side of the meter, that's when the customer's wire comes into play. So this is the load side of the meter. So customer, all this is customer stuff.
Gotcha. Okay, I think so. Don't think of primary, secondary as whoever's owning what. Think about it as down upstream is secondary and downstream. Oh, sorry. Upstream, which ways? I'm thinking of the wrong. One way is primary and one way is secondary. It has nothing to do with who owns what. It's just one's downstream and one's upstream of
Correct.
that specific piece of equipment.
Correct.
Okay.
Yeah, upstream, downstream, load, line, primary, secondary. For now, those are all kind of interchangeable concepts.
Okay.
Yeah. And what you see highlighted in red is normally customer owned here. So,
Gotcha.
utility would own coming into the meter itself.
Gotcha.
It's a great question. Before I delete or erase any of that, do you have any additional questions on that?
I don't think so.
Okay. And for the record, people on YouTube, don't just draw lines in Revit. Do the right way. I don't have anything loaded since this is a base, like out of the box type thing. But do it right, please. Panel schedules or panel boards. That's what I was going to do. All right. So we just dropped in these panels and this transformer. So let's go ahead and name these and define these, right? So I've already that's already defined as 208 distribution system, which is fine. Two lugs, max number of single breakers, 12 is probably going to be fine. Panel name, there we go. So this is going to be let's call it LP1. And we'll call this HP1. I can not fat finger, there we go. And we will call this TX1. All right. And right now we're just going to ignore let's go ahead and change it to 3R since it's outside. These are surface mounted. They are not recessed because they are mounted on the surface and not recessed into the wall. Right. So from here, because we've got it, okay, so quick recap. We've already got everything laid out. Now we're adding this stuff. So let's go ahead and set this up and then we will start circuiting our receptacles and whatnot. So I want to power this. You can select the panel saying that. Not assign. Oh, okay. So it's saying, hey, I can't assign this because the secondary distribution for TX1 is not set. So this is the distribution, meaning incoming. But the secondary, where the load side, should be 208. All right. And now I should be able to go, that's the one I want.
You did mention that this specific client wanted the 480 277, right?
That is correct. Yeah. They want to be able to power everything at 480 volt. So that's why we're sitting a 480 volt panel running circuits, lighting circuits. They've also got a welder and a couple other things, which we're not going to get into. We're not going to show it here, but there will ultimately be additional things on this 480 volt panel. That's why it's a panel instead of just a disconnect. So we name that. Got the distribution. Okay. So let me show you all a cool trick. So if you go to View, Use Interface, you can go to the system browser right here. It's over, plug it in there. Go close this out since we don't need that right now. All right, so this system browser shows you mechanical, electrical, plumbing, all the stuff that is in here. All right, so I just want to show electrical things. All right, so right now I've got this system saying, hey, like I've got LP1 powered by TX1 powered by HP1. Right? And in my unassigned, I've got a bunch of receptacles and lights. So and of course HP1, because the line side of HP1 is not circuited to anything. I guess I could do it to nothing. Let's see if that'll actually work. There we go. All right, so it's an unnamed circuit now. There we go. All right, so as I start doing these receptacles, you're going to see them go from here and drop down into the LP1 circuitry. Right? Now, normally you don't want more than 6-ish receptacles on any single circuit. We have way less than that, but what I'm going to do is kind of break it up just so we can see more circuits on this thing. So I want this thing to go to LP1. Same thing with these. 1, 1. Put that one on its own. And we'll just put all 4 of those on their own. And as a quick shortcut, people on YouTube, you can actually change. So you see where it says power and then AA in parentheses. You can change the keyboard shortcuts to make things easier. Most of the keyboard shortcuts that I use are all on my left hand. So instead of having to come up here each time, I can just type AA and it automatically circuits them. Okay. So we've got all those. Let's go to our lighting plan and circuit those things. Now at this voltage, we could literally put all of these on a single circuit and just put in multiple lighting switches, but still have everything powered by a single breaker. There's nothing wrong with that. So now we have everything unassigned has been circuited. We've got everything in there circuited the way we want. Let's go look at the panel schedules. So we're going to create a panel schedule. We'll just use the default template, see what that looks like. So for now, that's all fine and dandy. Let's go look at what our 480 volt panel schedule looks like.
Is there ever a good reason to separate the lighting into separate breakers instead of putting them all on the same one?
Yes, a couple of them actually. So first of all, obviously load. So if you have a large quantity of lights, then yeah, break them up. If you have a large area of lights, it's also a good idea to break it up. Meaning, if you could theoretically put 50 lights on a single breaker, but that covers 5 different rooms, okay, they're like massive rooms. I'm thinking a specific case where we did a courthouse. The lights were nothing. Like we hardly poured any power on the lights, and we literally could have done about 5,000 square feet on a single breaker, but it just didn't make sense. Like if that breaker trips, the entire floor goes down.
The entire buildings. SOL.
Yeah, exactly. So it's like, okay, do we have to do this? No. Does it make sense from a practical standpoint? Yeah, let's go and break it up. So we did, 4 or 5 different breakers. They were very lightly loaded. But if something trips because, a rat got into a light switch, the whole level is not going down. So does that answer your question?
Yes.
Okay, cool. Actually, I do want to do that. Let's do that and that. Okay. All right, so I'm going to get rid of this for now since we've got everything circuited, so we're good there. Make this a little bit bigger so that you can see it on YouTube. and there. Okay, so I did this intentionally. All right, so you generally start with your lower voltage panel boards when you start looking at this. All right, it's just the easiest way to do it. Go from there. So you start at the top, fill in your location. If you're actually doing a full-fledged project, people on YouTube use what are called spaces. Okay, there are rooms in Revit and there are spaces in Revit. Rooms are for architect, spaces are for MEP. MEP world can pull information out of spaces. Literally no difference between the two other than one is for one and one is for the other. Location here will automatically fill in if this panel board is located in a space. The space will also show up here automatically if this receptacle is located in a space. So if you're doing a real world project, try to use spaces because it makes things much easier. Right? So we've got supply, surface, 3R, so that's all correct. Bolts, that's all correct because we are actually using 4 wires. AIC rating. So out here, I just happen to know our AIC rating is going to be very minimal. So we'll just call it 22. And it should be more than enough. Let's do 22,000. Or the panel schedule I'm used to automatically fills this in. All right. So the reason, actually, are you familiar with what AIC ratings are? I'm pretty sure we went through it, but I'm going to ask you again.
If we did, I don't remember.
Okay. AIC stands for ampere interrupting capacity. So when you have a bolted fault, we'll just call it that, you can think of it like there are 3 copper bus bars and somebody drops a 2-inch bolt on them, a bolted fault. Something that can handle a massive amount of current. Well, how much is that current for however long it can handle? It's typically about 3 to 10 cycles. It's going to be in the thousands range typically. Even if it's for a very short time until something, a circuit breaker opens or a fuse blows, it's going to be massive amount of current because there's ultimately very, very, very little resistance. And we know that V is equal to IR, but if we're looking at I is equal to V over R. And if R is really small, that means I is very large. Okay. Tracking that so far? Okay.
Yeah.
I know that was kind of weird, but just know that when there's a bolted fault, you've got a stupid amount of current. Now, the AIC ratings, there's no standard on them. Other like some equipment comes in, actually some HVAC equipment comes in like 5K AIC. And there's a lot of panel boards that come out at like 10 or 11, 22, 24, 35, 65. Like it's kind of all over the place. There's no like, oh yeah, these are the standard steps for each manufacturer. That's not how that works. So most of the time we'll say, the minimum AIC rating. And that means that this panel board can handle physically 22,000 amps opening. Like I can open 22,000 amps and stop this fault from occurring. When you have that many amps flowing through there, 20,000, 65,000, whatever, there's a lot of magnetic force and a lot of ability for that arc to jump free air. So like when the circuit breaker opens, well, there's only so much space between each chunk of metal. And if there's enough amps there, it can still jump that arc. I'm sorry, it can still arc that free air space. And if you don't have it rated properly, either your panel board would be crushed due to the magnetic forces, or even though the circuit breaker is physically open, current still passing through it because of the arc. But assuming I've got a valve in the water world, if I close the valve, but the pressure is so high that it still pushes through the valve, starts leaking, well, the valve's no good, right? I need a stronger valve, something that can handle more pressure. Like I don't think that actually happens in the real world. That's the concept.
Yeah.
Great. Increase the pressure. Increase the ampere interrupting capacity. Increase the flow interrupting capacity of this valve. there's a lot of good articles out there. If you watch this like 10 times and my explanation doesn't make sense, simple Google search. Anyways, so since our main type is MLO and for some reason it come in automatically, we'll just throw it in there. Just go ahead and close this out for now. All right. So on MLO panels, obviously there is no main circuit breaker rating. There's no main circuit breaker at all. So what you can do here is you can go to Manage, Panel Schedule Templates, Edit a Template. And I want actually, let's create a new one before I do that. Manage Templates, and I'm going to copy this one, call it MLO. Go. Okay. So manage panel schedule, edit a template, and I'm going to now go edit that MLO branch panel. Dang it. Working. There we go. This is how you edit a bunch of stuff. Really awesome,
Wow.
really helpful. You can code quite a bit of stuff in here. But since there's no MCB rating on an MLO panel, I can actually get rid of this.
Is this template your template, or like a specific Revit template, or is it like our company type template?
What you've been seeing this entire time is literally an out of the box, start from scratch. All I did was throw in a couple walls and load a couple families.
Gotcha.
So yeah, for the people on, obviously here at our company, you will see a much more, many more of the templates of the panel schedules, and people on YouTube, you will hopefully see panel schedule templates on your company. So
is the panel schedule template linked to the family, like associated with the like piece of equipment, like for example, the panel, obviously, is this linked to the panel family? So whenever you load in a panel of like
like LP1 panel?
Yeah, the schedule, the panels, the schedule loads in too, because we already have a template, like a panel template associated with that family. It's not something extra that you have to like add in, like it automatically comes in when you add in a panel from our panel families.
Actually, no. That is not an accurate understanding. The panel boards over here do not have panel schedules associated with them. The panel schedules that live here live in the model itself, regardless of what you bring in.
Okay.
Now, there's way to do transfer project standards, which means that you can take whatever you've built here and move them to other projects. So that's how you would get panel schedules that you make into other projects.
Gotcha. And how you associated the panel with the panel schedule is by the space, the space that you're creating. Is that how they're related? Like, is that how it's connecting? Is to get since the panel itself is not associated with a specific schedule, are you is it the space that's making them, like, is creating a space in Revit what's pulling the information from a specific panel and putting it on a schedule?
Okay. So there was a step in here that I kind of flew past. Let me show you here in just a second to answer that question. Yeah. You know what? Let's just go ahead and do it now. Yes, that's fine. Let's just delete this panel schedule. Let's go to site plan. Let's go to power plan actually. And let's delete LP1. Okay, so our panel schedule LP1 no longer exists. So if I wanted to create a panel schedule, go up here, create panel schedule, and then I can either use the default, which is the one that it just was, or I can choose a template. Here I can choose whichever one, the default one that came with Revit, or
the one
I literally just created. Yep.
Okay.
So I'm going to say that one, and that's where this comes up.
Okay.
Notice that, we lost the information that we typed in here because this was plain text. When we put in 22K and MLO, it stayed because it was associated with the panel itself. And then since I chose the one that I just created, the MCB rating is no longer here.
Because you use this specific template. Okay.
Exactly. Yep. Does that answer your question?
Yes, it definitely does. I
Okay,
was like,
cool.
oh, is it just automatically there? And you just, oh, look, schedule.
Yep. No, you got to create the schedule. And surprisingly enough, you can actually do that for like, I guess you can't do it for transformers anymore. You used to could be able to do it for that. But yeah, any panel board, switchboard, stuff like that, there's always going to be a create panel schedules right here. So,
Gotcha.
So yeah, so we have covered the top of this, how to fill that out. If you think of anything, questions, let me know. Next time for the people on YouTube, we're going to go through the bottom half of this relative, like why is this layout bad, 6, 5, and 9, how to balance
balanced.
panel board, so on and so forth.